Hi guys, how you doing today? Hope you're doing great. You ever have one of those days when you just like discover that you thought you had you had something like completely nailed down, and then you take another look, or someone else takes another look, and you see loose ends everywhere? Oh, I ended up deleting a big chunk of the next laboratory by accident. So and I don't have a backup because it's composed on the internet. So now I gotta write it again. Isn't that awesome? Um, don't worry, I'll get it done, and it'll be better. It'll be better this time than the first time, no doubt about it. All right, gang. So today, let me tell you, remind you of the exam coming up on Monday, covering Newton's laws of motion and work and energy. All right, and so that's coming up on Monday. It's the same format as before. There'll be multiple choice questions. There'll be quantitative problems that you need to work out on paper and submit your work by taking photographs of your work and submitting them on the assignment, the exam assignment, attaching them to that assignment. And I'll proctor it via Zoom, just like I did last time. And what I need you guys to do is be able to show me your work area while you're working. So the best way to do that is Zoom on your cell phone, put your cell phone somewhere to the side, and with the camera projected onto your work area so I can see that you are abiding by the parameters of the exam, which is closed book, closed notes. You can use the equation sheet, which is provided, and you can have a calculator, of course. You need a calculator. You should have a calculator. And we're all abiding by the tenets of academic honesty. Okay. So it worked pretty well last time. We're going to do it again. All right. So that's coming up on Monday. Now I have an announcement to make for you guys. Rest in peace, Dr. Croft. What does that mean? I'm not sure what that means, William. Did I die? um, I have an announcement to make. So I decided that for the final exam is cumulative, and it counts as 20% of your grade. And so what I decided to do was to sort of double its impact, potentially. Double its impact, but only if it's a good impact. And so the way this will work is you'll take your final exam, you'll get a score for your final exam. If the score you get on the final exam is higher than the grade that you got on one of the previous 3 exams, then that final exam score will replace that previous exam score. Okay? I did this last semester. Sort of I don't know, it's a form of grace to take into account that we're in extraordinary times right now, and there's difficulty associated with that. So it's a little bit extra flexibility. Yeah, all the work I did. Yeah. It was like the hardest part too to code up because I'm like have to typeset stuff, equations in HTML, and that's a bear to do. So the final exam can potentially increase your score. It counts. The final exam is 20% of your grade. All right. What I'm saying is that if you score higher on the final exam than you did on your first exam, second exam, or third exam, that score will replace that earlier exam score, and thus boost your average a little more. The final exam is cumulative, so it's testing you on the same material again. All right. The other thing is what I'm going to do is on the homework. You got all these homework problem sets. I will, similar to the way I do this in lab, where I drop your lowest grade, I am going to do something analogous with homework. It's a little bit more tricky because homework, they're not all the same number of points. Um, and they're approximately the same number of points. So I haven't decided exactly how I'm going to do this mathematically, but effectively what I'm going to do is drop your lowest grade in the homework category as well. You know, again, extraordinary times. I think it's harder for people for students and professors to keep all their ducks in a row these days. Um, in other words, one homework assignment is doing poorly on one homework assignment won't break you this semester. What if it is lower than all the other exam grades? It won't replace any of them, but will still be counted as the fourth exam in the overall exam average, right? So exactly, Holly. So if your final exam, like let's say you do 80s on exam 1, 2, and 3, and you get a 70 in the final exam, that final exam score holds as a 70 and gets averaged in with the rest of your exam scores, but since it's not better than any of your exam scores, it doesn't replace any of your previous exam scores, okay? So, in other words, this can help, but it can't hurt, all right? It can help your grade compared to you not doing this, but it can't hurt your grade. All right, so I want to do clicker questions today. And it's been a while since we did this. Before I do that, I posted a second video tutorial for you guys this morning. And so that is on YouTube, and it's linked to, now I better check. I'm all over the place today. Let me check this quick. I think I posted a link on Sakai. Under lessons, week 8. Yes, so I had the video tutorial for potential energy, and I posted a new one this morning for good morning, physics Scott, for the Atwood's machine problem. Okay, so that video tutorial will help you make sense of the Atwood's machine problem that was assigned to you in homework. So that problem set is due Thursday in the PM. Okay, so you still have almost 2 days to finish it, but don't forget about it. All right, make sure you work on it. So these are the two problems I think are the most challenging, and so I did the tutorials on these two. All right, are we having in-person class Friday? Yes, we are. Yeah, that's I'm glad you said that, Maddie, because we don't usually have in-person class on Mondays, but we will on Monday. I guess that's the other piece here, is if you choose to, I'll have to add that to the sign-up sheet. So I'm really glad you said that, because it's not on there. The sign-up sheet for meeting in person, I'll add Monday to that, and if you prefer to come to the lab to take the exam, just like was the opportunity last time, you can do that. But there's limited space, so I'll have to do it on a sign-up basis. So I will create the sign-up and then post an announcement about it when it's done, and when you can go there to sign up. All right, so then, yeah, if you want to come to the classroom, the laboratory on Monday to take the exam, you can do that. All right, but yeah, we will have in-person class on Friday. A recitation session, and I'll Zoom like I did last time. I don't know how effective that is. It's not the best projection system, but if you can't make it in person, you can tune in on Zoom to be part of the discussion. All right, so you guys ready? Let's do some clicker questions. We will go to, let's see. I just need to find the right tab here. Huh. Hold on. Darn it. What the heck? There we go. Okay, so sorry, I wasn't getting the right source for my video here. Oh, come on, what the heck? There we go. All right, so we're back. So the we'll use this generic poll on Poll Everywhere. So like last time, you should be able to go to. Let's make this a little bigger. But now you can't see it. Jeez. Never mind. I was trying to make the text bigger so you could see it, but it doesn't really work that way. Well, at least one of you is there already. So you can go to pollev.com, Jeffrey Groff 336, and or you can text Jeffrey Groff 336 to 37607 to join, and then using text messaging you can text A, B, C, D, or E to that number. And some of you did that last time, and I think it worked really well. So those are the two options. So go ahead and do one of them now, and then cast a vote, A, B, C, D, or E, and I'll give you guys like 2 minutes to see if it's working. Here we go. So I got 18 of you on the live stream, and I got 3 of you, 4, 5. Good. pollev.com/JeffreyGroff336 or text Jeffrey Groff 336 to 37607 and then cast your vote. Alright, we'll come back to this. There's only 6 of you on here, and there's more than 6 of you out there. But let me ask you some questions, and then you can start responding. Okay. So, well, we did this one already. Let's go through some of these quickly. A ping pong ball is shot into a circular tube that is lying flat on a tablecloth. When the ping pong ball leaves the track, which path does it follow? 1, 2, 3, or 4? A, B, C, D, or 5, or E? Which path does it follow? You're looking down from above. Which path does it follow? 1, 2, 3, 4, or 5? Okay, good. All right, so what I'm seeing is, I'll show you a snapshot. So this is what I'm seeing, your responses. B is your favorite. But there's a few votes for the other things. So look at that. You're changing your vote. And so what's going on here? B is the best answer. Once the ball leaves the tube, there's no longer a force to keep it going in a circle. Therefore, it simply continues in a straight line. It's Newton's first law. Newton's first law. So a better way a better way from physics perspective of framing this question is, well, a ball that's rolling on a tabletop should just want to go in a straight line. It doesn't want to go in a circle. So a better way to frame this is, what compels it to go in a circle in the first place? And the answer to that is this tube that it's in, because the walls of the tube exert a centripetal force on the ball, which causes it to move in a circle, a center pointing force. So when that tube is no longer there, the ball resumes its natural state of motion, Newton's first law. A body in motion will continue to do so in a straight line with constant speed, i.e. constant velocity, unless it's compelled to change its motion by an external force, an external net force. Okay? So 2 is the best answer. All right, next. Let's skip ahead a little bit. Let's find a good one here. This is an interesting one. What can you say? Here, I'm going to reset the poll. Clear all responses. All right, it's completely reset now. What can you say about the force of gravity acting on a stone and a feather? Hold on. Did I skip one? Well, sorry, you probably can't read this down here, but it says evacuated tube, a feather and a stone in a vacuum. And what can you say about the force of gravity acting on them in that situation? Looking at your responses, but I'm not going to show you what you say. This is interesting. So there's no air drag. I'm so bummed about that quiz or not the quiz, the lab. It involves air drag, and I can't believe I deleted all that. What can you say about the force of gravity acting on a stone and a feather in an evacuated tube? So a lot of you are picking, let's see, B, C, and D. B, C, and D are your favorite responses. I bet if I asked this question using a synonym, you guys would change your votes. Well, unless you're already correct. All right, but I bet a lot of more of you will get correct. Will become correct. All right, so here we go. You ready? Synonym. In physics, force of gravity is synonymous with weight. The weight of an object. You remember how we calculate it near the Earth's surface? The weight of an object is its mass multiplied by g, mg. Force of gravity is synonymous with weight. So put that synonym in there. What can you say about the weight of a stone and a feather? Wow, look at that. It's amazing how one word can just completely change your perspective. There you go. It's amazing. It's almost like we're programmable. One word can just, it's just amazing. Weight. Force of gravity is synonymous with weight. Good. So, all right. So now, you guys, your favorite answer is B. B. The force of gravity is greater on the stone. Great. So, what was going on? I think many of you were answering this question. This question. What can you say about the acceleration of gravity acting on the stone and the feather? Oh, hold on. Let me clear the poll. All right. Good to go. If you guys aren't able to get on the poll anywhere, but everywhere, you can also put answers in the comments. It's not anonymous, I suppose, but I don't know. You can be brave. Okay, so your favorite answers here are, let's see, C and D. Your favorite answers are C and D. C and D are your favorite answers. So let me ask you this. All right, this is going to cause some of you to change your answers. All right, and some of you already have. But let me ask you this: the force of gravity between objects is something that is a result of mass. And we've looked at this a little bit, and you'll see this again next week. Is Newton's law of universal gravitation is a general way of describing this attraction between masses. And near the Earth's surface, the force of gravity, you can just think of it as the weight of the object as its mass times g, the acceleration due to gravity. The evacuated tube, does the presence or absence of air have any bearing on gravity? Or the effect? Or does it have a bearing on the net effect that gravity has? So if I take the air out of a cylinder, does that mean I've also taken the gravitational force away? All right. Does the rock and the feather still have weight, even if there's no air? Yes. Yes, it does. So the best answer here, the only answer here, is that the weight of these two objects is not the same. But what we learned in class is that the acceleration due to gravity, the effect that gravity has, is the same. So D, it is equal on both always. The acceleration due to gravity is 9.8 meters per second, meters per second squared. And that's true of, it doesn't depend on mass. All right. So the best answer here is D. It's equal on both. All right, so I'm going to clear the results, and we're going to go on. It's a good one. This is a good one. This is a real good one. All right. So the poll is clear, all right? And a block of mass, it could be a person with mass m rests on the floor of an elevator. This is a while ago. It's been a while since we talked about elevators and forces. But we talked about this situation. And so connect what you know about this experience of riding in an elevator, accelerating up, accelerating down, and this question. It's moving upward at constant speed. What is the relationship between the magnitude of the force due to gravity and the normal force on the block? So these forces aren't shown here, but you could draw a free body diagram, and there'd be a force pointing up, and that's the normal force, the floor pushing on the mass, and then there'd be an arrow pointing down, which is gravity, the mass's weight. Okay. What's the relationship between these forces if the elevator is moving upward at constant speed? Let's see. I got a couple of responses. This is interesting. This is real. I'm watching the bars change as votes come in, and trying to see if there's any pattern in the way you're responding. Okay, now it's time for me. Okay, good. Okay, so let me see if I can get more of you to the right answer. All right, and it goes something like this. The problem is talking about motion at constant velocity. All right, constant velocity. Okay, so that's one thing. That's probably important. The other thing we know is that we could, if we drew a free body diagram to represent the forces acting on this mass, whatever it is, in the elevator, that free body diagram would have two arrows. It would have one pointing up for the normal force and one pointing down for the force of gravity, i.e. weight. Okay? Constant velocity, two forces pointing in opposite directions. Normal force, gravity. Constant velocity, two opposing forces. What does constant velocity tell you about acceleration? It tells you acceleration is 0. What does Newton's second law say? Net force, the total force, equals mass times acceleration. So if acceleration is 0, the net force is 0. So what has to be true about normal force pointing up, gravity pointing down, so that those two forces add to 0? What has to be true? I'll give you 10 more seconds. See if you, I think if you change, yeah, okay, change your vote. Okay. Okay. That's interesting. Okay. So let me clear those results. And let's look at the correct answer here. So most of you are getting there. If you have two forces, one pointing up and one pointing down, and the total force is 0 because there's 0 acceleration, those two forces must have equal magnitude. They must, one is positive, the other is negative, but their magnitudes cancel. Their magnitudes are the same. All right. Similar question, different situation. Same mass, same elevator, but now it is accelerating upward. It is accelerating, and the acceleration is directed upward. All right? It's not just moving upward, it's accelerating upward. What's the relationship between these forces now? Excellent. Interesting. All right. So you guys can keep voting while I'm talking here. Um, so there was this really interesting phenomenon that just happened. All right. So initially, so I think what you guys know is if the system is accelerating, then there must be an unbalanced force. And so you have these two forces. One's pointing up and one's pointing down. Why can't I get my head straight? One's pointing up, one's pointing down. And if the system is not accelerating, they cancel. They have the same magnitude. But if the system is accelerating, then when you add these two vectors together, you get something that's not zero and has a direction, the net force, the total force, that points in the same direction as the acceleration. So in this case, I think you guys get that idea that if the system is accelerating, there's an unbalanced force. So they're not equal. And what I noticed is that the initial responses were picking A, and then there was a bunch of responses that came in which were picking C. So both of those options are recognizing that there's an unbalanced force. One of them is correct, though, the other is not, and it has to do with the direction of the imbalance. All right? So if you're accelerating upward, the net force points upward. And you have a normal force that points up and gravity that points down. And if you add those together and you get a net force, which is up, which one's bigger? The one that points up or the one that points down? The normal force or the force of gravity? So, all right, you're moving in the right direction now. Good, 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 good. All right, so yeah, the correct answer is A. The block is accelerating upward, so it must have a net upward force. The forces on it are Fn up and Fg down, so Fn must be greater than mg in order to give the net upward force. And so now connect this to what you know. There's a follow-up question there. What you know about riding on an elevator. If you're riding on an elevator that's accelerating upward, remember we talked about this, you feel heavier. You have this sensation of being heavier. Or if you're in the elevator and it's accelerating downward, you have this sensation of feeling lighter. And in fact, if you stood on a spring scale, the spring scale would decrease its reading. And you're not actually heavier, you're not actually lighter. It's you just feel lighter because the sensation of weight, our sensation of weight is due to the normal force, the floor pushing on our feet. All right. And if you're accelerating upward, the floor pushes on your feet harder than your weight, so you feel heavier. And if you're accelerating downward, the floor pushes on your feet less than your weight, so you feel lighter. All right. Let's continue. If you guys have any questions while I'm doing this, put them in the comments. Here we go. We'll do a couple more and then let's see. We'll do two more and then we'll switch to energy for a while. All right, let's take a look at this one. Let me clear the responses. So you have two identical blocks, one resting on a flat surface and the other one resting on an incline. For which case is the normal force greater? Case A, case B, both the same. There's three for both the same. And similar conditions. Normal force is equal to weight, normal force is less than the weight but greater than zero, or the normal force is equal to zero. Okay, so those of you who chimed in quickly, you're getting this right. Okay, those of you who chimed in quickly. I guess you guys can't see the responses. Maybe you can. Of course you can. Well, I don't know. All right. Yeah, I'm not sure if you can see the responses as you're chiming in, but um, so you remember. So here we have an incline. Let me. One way you can think about. One way you can think through problems conceptually is you can think about limiting cases. Okay, so if you have something resting on a flat surface, there's a normal force because that surface supports it. And if you start increasing the angle of incline, and the question is what's happening to the normal force, you can say, well, what happens in the limit where the angle of incline is vertical? So if the angle of incline is 90 degrees, what's going to happen to that thing? Is there going to be a force of contact between it and the surface any longer? No, it's just going to fall in free fall. So the normal force starts at some value and then goes to zero. Okay? And that should be all you really need to know to answer this question. If it starts at some value and goes to zero, then that means this is the maximum normal force, and it decreases as the angle increases until it gets to zero. The normal force, the force of contact. I mean, you could be more quantitative about this. You could study, the actual normal force as a function of the angle of incline, and you would see that it depends on trigonometry. It depends on the cosine of the angle of incline. And so that we've done that. We've done that in these problems involving inclines. We see that over and over again. The normal force is a function of the cosine of the angle. So the cosine is maximum at zero and goes to zero as the angle increases to 90 degrees. All right, so the best answer there was A. Case A. All right, one more. We're going to do, on Friday, we'll do more of these, okay? I'm starting to rethink Friday now. I got to think on this. If we do, I'd like to. Let's still do it in person, and I can field questions that you have about problems, and then we will use the rest of that time on Friday to do more concept questions like this, and we can do that in the lab just like we can here. All right. But back to, all right, let's take a look at one more in this set. All right, here we go. Clear your responses. And here we go. You tie a rope to a tree. You pull on the rope with a force of 100 newtons. What's the tension in the rope? You pull on the rope with 100 newtons of force. What's the tension in the rope? All right. Great. Okay. So you guys are picking C. This is a Newton's third law problem. If you pull on the rope with 100 newtons of force, the rope pulls on you with 100 newtons of force in the opposite direction. Action-reaction force pairs have equal magnitude, opposite direction. Okay, so let me ask you a different question. Here I think you guys nail this because you guys are like, well, everything's stationary. When you have problems, it's like with this concept, it's like a problem like this. All right, so I think you guys will do better on this now because we just did that problem. But this is a similar situation. You have a collision between two objects. One is more massive than the other. Let me clear your responses, and then you vote again if you already did. A small car collides with a large truck, which experiences a greater impact force. Thanks, William, for telling me that all you see is your own. That's helpful for you and me because you guys won't be. It's completely anonymous. I don't know. I get better response rates when it's anonymous. Okay, so one person picked E. At least one person picked E, which is actually not a bad answer for here. No, sorry. I'm thinking of a different question. No, E is a bad answer. The only answer here is C. C. Both are the same. The car collides with a large truck. Which one experiences a greater impact force? Newton's third law. Newton's third law. Let's define the action as the truck hitting the car. The reaction is the car hitting the truck. Newton's third law says the force the truck exerts on the car is the same as the force the car exerts on the truck. They have equal magnitude but opposite direction. All right, these are action-reaction force pairs. So C is the correct answer. And what I was getting at, though, is maybe you're answering this question. In a collision between a car and a truck, which has a greater acceleration? And the answer here would be the car. Well, you could pick E. It depends on the mass, but typically cars have less mass than trucks. All right. Let's see if this opens. Nope. Hold on. It won't open. There we go. All right, so you have a car, you have a truck, and they collide. The car, the force on the truck by the car points in that direction. The force on the car due to the truck points in that direction. Newton's third law says that those two forces are equal in magnitude, but just opposite in direction. So there's a negative sign right there. Equal in magnitude, but opposite in direction. So what we're getting here, though, is that Newton's second law is force equals mass times acceleration. So acceleration is force per unit mass. All right, so that's the effect that the force has. The acceleration is the effect that the force has. And so the car is going to have a much larger acceleration because it has a much smaller mass. All right, but that doesn't mean the force is different. Force is the same. The force of collision is the same. From the perspective of the truck, the perspective of the car, it's the same. They're both experiencing that event. The force is the same. But the effect that that force has is different because the car is going to accelerate it much more because it has a smaller mass. Acceleration is force, which is the same, divided by mass, which is different. So the car has a smaller mass, therefore it has a larger acceleration. All right, we got 5 more minutes. Let's see if we can do a few of these from a different... oh shoot, I just closed the wrong one. Hold on. Let's try this. All right, so let's do a few questions about work and energy, okay? Let me clear the poll here so I can watch what you're doing. Is it possible to do work on an object that remains at rest? Is it possible to do work on an object that remains at rest? This might seem like a trick question. The best way to approach this question, you guys are split exactly 50-50. But the correct answer, you guys are split 50-50, but the correct answer is no. And why is this? Well, remember work equals, well, we could write it as the integral of F dot dr, or if the force is constant, it's in one direction, work equals F dot displacement. But any way you think about it, work is a function of displacement. Displacement means the thing is moving from one place to another. So you can't do work, you're not going to do work on an object that remains at rest. And so one that maybe this is why, this might be confusing, because maybe you think like, let's say that there's like an immovable object, a giant boulder, and you go up and you push on it, you're like, man, you can exert a lot of force and you can do a lot of work in that sense to try to move that thing. But the thing is, the question isn't like, are you doing work? Is your muscles doing work? And like microscopically, your muscle fibers are moving and your joints are moving. So I mean, you are what is work? Converting energy from one form to another while you try to push that immovable boulder. But the question is, are you doing any work on the boulder? You're doing work on your muscles and on your joints and on your bones. You're doing work on all those things. There's forces exerted and there's displacements happening. But that boulder doesn't budge. You are doing zero work on that boulder. It is not gaining energy or losing energy. It is stationary. It's just staying there. All right. We got one more minute. Let's see. Let's see what you guys do with this one. All right. This will be the last one for today. There's this box being pulled across a rough floor. So interpret that to mean that friction is important. Friction in this picture is F, and the box is being pulled to the right. What can you say about the work done by friction? Is it positive? Is it negative, or is it zero? Good. All right. Let me show you the correct answer. But most of you are getting there. What is the meaning of the dot product? The dot product can be interpreted geometrically in terms of the cosine of the angle between two vectors. So if you have one vector, in this case the friction vector pointing to the right, friction opposes the effort to pull, so it's going to point to the right, and the block is being displaced, left, and it's displaced to the right. You have a displacement vector and a force vector, which are at 180 degrees relative to one another. What's the cosine of 180? -1. So friction is going to do negative work. What does that mean, like energetically? It means that negative work means that energy is being, well, in this case, it's a non-conservative force, friction, so negative work done by a non-conservative force means mechanical energy is being stripped away from the system. Mechanical energy is being taken away from the block. And it's being dissipated as heat, thermal energy in the environment. So that's the meaning energetically of negative work in this case. Energy is leaving the system, and the system is this block. All right, so that's it for today. That's it for today. We'll convene Friday in person and via Zoom in the classroom, in the laboratory on campus, and I'll take some questions if you have them, and we'll continue doing more concept questions after that point. All right, but all these concept questions are posted. They're linked to in the lesson for week 8, and it's really beneficial to study these. Okay. All right. Enjoy the rest of your day.